Imagine a cosmic lion, its blazing eyes carved from the skeleton of a dying star, its mane a swirling halo of stardust frozen in time. This is NGC 2392, the Lion Nebula, captured in stunning infrared by the James Webb Space Telescope. At its heart lies a white dwarf, a scorched remnant of a sun-like star, blasting radiation into the surrounding gas and dust, sculpting the nebula's fierce visage. The lion's face, etched by stellar winds, glows with the heat of a dying star, while its mane stretches outward in a chaotic dance of cosmic debris. Each filament, each glowing knot, is a testament to the violent rebirth of matter after a star's final breath. This isn't just a portrait of death, it's a gallery of creation, where the ashes of one star forge the seeds of new worlds. Webb's infrared eyes reveal a story millions of years in the making, a celestial masterpiece carved by the relentless hand of stellar evolution. In the vast expanse of the cosmos, a new image has emerged that captures the haunting beauty of a dying star's final act. The James Webb Space Telescope has revealed an infrared view of NGC 2392, a nebula known as the Lion Nebula, where the remnants of a sun-like star are sculpting a cosmic lion's face. At its heart, a scorching white dwarf star is unleashing intense radiation, carving intricate patterns into the surrounding gas and dust. This process has illuminated a sprawling mane of surviving material, creating a striking visual of a celestial predator in its final moments. This discovery offers a rare glimpse into the dramatic end stages of stellar evolution, where a star's death reshapes its surroundings into a luminous masterpiece. To understand this image, we must first step back and consider the life cycle of stars like our Sun. Most stars in the universe, including our own, will eventually reach the end of their lives. After billions of years of fusing hydrogen into helium in their cores, these stars expand into massive, cool red giants. Their outer layers begin to shed, forming a glowing shell of gas and dust that drifts away into space. What remains at the star's core is a dense, Earth-sized remnant called a white dwarf, a stellar ember still burning with leftover heat. This white dwarf, now the central figure of NGC 2392, is the architect of the nebula's haunting form. The Lion Nebula, NGC 2392, is a planetary nebula, a term that might sound misleading. The word planetary here refers not to planets but to the nebula's round, glowing appearance when viewed through early telescopes, which resemble planetary disks. In reality, these nebulae are the final acts of stars like our Sun. The process begins when a star exhausts its nuclear fuel, causing its outer layers to expand and cool. As the star sheds its outer layers, the exposed white dwarf begins to emit intense ultraviolet radiation. This radiation interacts with the surrounding gas and dust, ionizing it and causing it to glow. The result is a luminous shell of material, often shaped by complex interactions between the star's radiation, magnetic fields, and the motion of the ejected material. In the case of NGC 2392, the white dwarf's radiation is not just illuminating the nebula, it is actively sculpting it. The infrared image captured by the James Webb Space Telescope reveals a lion's face, with a dark, central eye and a glowing mane of dust and gas. This intricate structure is the product of the white dwarf's intense light pushing against the surrounding material. The nebula's central region, where the white dwarf resides, appears as a bright, almost glowing eye, while the surrounding gas forms the lion's mane. The contrast between the dark, shadowy regions and the luminous filaments creates a striking visual that has captivated astronomers and the public alike. What makes this discovery particularly remarkable is the role of the James Webb Space Telescope in revealing such details. Unlike previous telescopes, which primarily captured visible light, Webb's infrared capabilities allow it to peer through the dust and gas that obscure much of the universe. Infrared light, which has longer wavelengths than visible light, can penetrate these dense regions, revealing structures that were previously hidden. This has enabled astronomers to see the fine details of the nebula's structure, including the intricate patterns of the mane and the sharp contrast of the central eye. The image is not just a beautiful snapshot of a cosmic phenomenon, it is a scientific breakthrough that provides new insights into how planetary nebulae form and evolve. The process of shaping the Lion Nebula is a testament to the dynamic forces at play in the final stages of a star's life. The white dwarf at the center of NGC 2392 is a remnant of the original star, now a dense, hot core that emits intense radiation. This radiation exerts pressure on the surrounding gas and dust, pushing them outward and sculpting the nebula's form. The interaction between the white dwarf's radiation and the ejected material creates the glowing filaments and dark voids that make up the nebula's structure. The lion's face is not a static image but a dynamic process, with the material continuously being pushed and shaped by the star's intense light. The mane of the Lion Nebula, which extends outward from the central eye, is composed of dense clumps of gas and dust that have been illuminated by the white dwarf's radiation. These clumps, which appear as glowing filaments in the infrared image, are the remnants of the star's outer layers. They are not uniformly distributed but instead form intricate patterns, suggesting complex interactions between the ejected material and the star's radiation. The precise shape of the nebula is influenced by factors such as the star's magnetic field, the velocity of the ejected material, and the density of the surrounding interstellar medium. These factors combine to create the unique, almost artistic structure of the Lion Nebula. Studying planetary nebulae like NGC 2392 is crucial for understanding the life cycles of stars and their role in the universe. When a star like our Sun reaches the end of its life, it does not simply vanish, it leaves behind a glowing shell of gas and dust that can persist for thousands of years. These nebulae are not just beautiful sights, they are also important contributors to the chemical enrichment of the universe. The gas and dust expelled by these stars contain elements heavier than helium, which are essential for the formation of planets and life. By studying the composition and structure of planetary nebulae, astronomers can gain insights into the processes that shape the cosmos and the origins of the elements that make up our world. The James Webb Space Telescope's ability to capture such detailed images of planetary nebulae is a testament to the power of modern astronomy. While earlier telescopes, such as the Hubble Space Telescope, have provided valuable insights into these objects, Webb's infrared capabilities allow for a deeper exploration of their structure and composition. The Lion Nebula's image, in particular, highlights the potential of infrared astronomy to reveal hidden details of the universe. By peering through the dust and gas that obscure much of the cosmos, Webb is uncovering new layers of complexity in the life cycles of stars and their impact on the universe. As we look at the Lion Nebula, we are not just witnessing the death of a star, we are observing the birth of new cosmic structures. The gas and dust expelled by the dying star will eventually disperse into space, enriching the interstellar medium and potentially contributing to the formation of new stars and planetary systems. This cycle of creation and destruction is a fundamental aspect of the universe's evolution. The Lion Nebula, with its striking form and intricate details, serves as a reminder of the beauty and complexity of the cosmos, and the ongoing processes that shape it. Through the lens of the James Webb Space Telescope, we are able to glimpse these processes in exquisite detail, offering a deeper understanding of the universe and our place within it. The James Webb Space Telescope, launched in 2021, has become a revolutionary tool for exploring the cosmos, but its journey to capturing the Lion Nebula was anything but straightforward. For years, astronomers had studied NGC 2392, a planetary nebula located approximately 4,000 light-years away, but its intricate structure remained elusive. The nebula, shaped like a lion's face, was only partially visible in earlier images from the Hubble Space Telescope. However, the true complexity of its form, its mane of dusty clumps and the scorching white dwarf at its heart, was hidden in infrared light, a wavelength that requires the unique capabilities of JWST to reveal. This chapter delves into the meticulous process that led scientists to this breathtaking discovery, from the telescope's design to the collaborative efforts that turned raw data into a cosmic masterpiece. At the heart of this revelation was the James Webb Space Telescope's ability to peer into the infrared spectrum, a region of the electromagnetic spectrum that is largely blocked by Earth's atmosphere. Unlike Hubble, which operates primarily in visible and ultraviolet light, JWST's instruments are optimized for infrared wavelengths, allowing it to detect the faint glow of dust and gas heated by the intense radiation of a white dwarf. The nebula's lion-like face, carved by the dying star's relentless energy, is illuminated by this radiation, but the details of its structure, its sharp edges, its swirling tendrils, and the delicate dust clouds that form the mane were only visible in infrared. This required a telescope with unparalleled sensitivity and resolution, and JWST's advanced technology made this possible. The mission to capture NGC 2392 began with careful planning. Astronomers had long suspected that the nebula's complex structure was shaped by the white dwarf at its center, but without the right tools, they could only speculate. JWST's near-infrared camera, NIRCam, and mid-infrared instrument, MIRI, were designed precisely for such challenges. NIRCam, with its high-resolution imaging capabilities, could capture the nebula's broad features, while MIRI's ability to detect longer wavelengths allowed scientists to peer deeper into the dust clouds that obscure the central star. Together, these instruments provided a dual view of the nebula, revealing details that previous telescopes could not. However, the process of capturing these images was far from simple. The nebula's faint glow required long exposure times, and the telescope's position in space over 1 million miles from Earth meant that every observation had to be meticulously planned to avoid interference from cosmic background light. Once the telescope was in place, the next challenge was to gather enough data to construct a clear image. Scientists targeted NGC 2392 during several observation campaigns, using JWST's powerful instruments to capture multiple exposures. Each image was a snapshot of the nebula's glow, but the true beauty of the Lion Nebula emerged only when these snapshots were combined. The process of stacking multiple exposures allowed astronomers to enhance the signal from the nebula while reducing noise, a critical step in revealing the intricate details of its structure. This required not only technical expertise but also patience, as the faint light of the nebula demanded hours of observation to accumulate sufficient data. The result was a series of high-resolution images that, when assembled, painted a vivid picture of the nebula's cosmic form. But capturing the image was only the first step. The real work began with analyzing the data to confirm the nebula's structure and understand its origins. Scientists used specialized software to process the raw images, adjusting for factors like atmospheric distortion and instrumental noise. They also compared the new data with previous observations from Hubble and other telescopes to identify changes over time. One of the most striking findings was the way the white dwarf at the center of the nebula was shaping its surroundings. The star's intense radiation was not just illuminating the gas and dust, it was actively carving out the nebula's lion-like face, a process that had taken thousands of years to unfold. By studying the distribution of dust and gas, scientists could trace the path of the star's radiation and model how it had sculpted the nebula's structure. This required not only advanced imaging techniques but also a deep understanding of astrophysical processes, from stellar evolution to the behavior of interstellar matter. The confirmation of the nebula's structure also relied on cross-referencing with theoretical models. Astronomers had long predicted that planetary nebulae like NGC 2392 would exhibit complex shapes shaped by the radiation of their central white dwarfs, but the level of detail revealed by JWST was unprecedented. By comparing the observed data with simulations of how such nebulae form, scientists could validate their understanding of the process. For example, the mane of dusty clumps surrounding the nebula's face suggested that the white dwarf's radiation had pushed the gas outward, creating a shell of material that had cooled and condensed into dust. These findings were not just observational, they provided critical insights into how stars like our Sun evolve in their final stages, shedding light on the life cycles of stars and the role they play in enriching the universe with elements essential for life. The journey to this discovery was a testament to the power of collaboration and technological innovation. The James Webb Space Telescope itself was the result of decades of research and development, with its instruments built to overcome the limitations of previous telescopes. But even with its advanced capabilities, the process of capturing and interpreting the data required the expertise of a global team of scientists. From the initial planning stages to the final analysis, every step involved meticulous work, from calibrating the telescope's instruments to refining the algorithms used to process the data. The discovery of the Lion Nebula was not the work of a single team but the culmination of years of effort by astronomers, engineers, and data scientists working together to push the boundaries of what is possible in space observation. In the end, the image of the Lion Nebula was more than a stunning visual achievement, it was a breakthrough in our understanding of stellar evolution. The James Webb Space Telescope's ability to capture this intricate structure has opened new avenues for research, allowing scientists to study the processes that shape planetary nebulae in greater detail. The nebula's lion-like face, sculpted by the dying light of a white dwarf, serves as a reminder of the universe's ability to create beauty from destruction. As scientists continue to analyze the data from JWST, they are uncovering new layers of complexity in the cosmos, each discovery bringing us closer to understanding the fundamental forces that govern the universe. The journey to reveal the Lion Nebula was a journey of patience, precision, and passion, a testament to the enduring quest to explore the unknown. James Webb has captured a striking new infrared view of NGC 2392, the Lion Nebula, revealing the dramatic aftermath of a dying sun-like star. At its center, a scorching white dwarf is blasting radiation into surrounding gas and dust, carving out the nebula's lion-like face while illuminating a sprawling mane of surviving dusty clumps. This part of our deep dive into James Webb captures a cosmic lion sculpted by a dying star focuses on go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. In the early days of astronomy, planetary nebulas were mysterious, glowing clouds that defied easy explanation. Ancient astronomers, like the Greeks and Chinese, observed these ethereal shapes in the night sky, noting their faint, colorful halos. But it wasn't until the 19th and 20th centuries that scientists began to piece together the story of how such celestial objects form. The key breakthrough came in 1910, when Ejner Hertzsprung, a Danish astronomer, identified the first white dwarf star, a dense, dying remnant of a sun-like star. This discovery laid the groundwork for understanding that stars like our Sun eventually shed their outer layers, creating the glowing shells we now call planetary nebulas. For decades, astronomers puzzled over how these delicate, symmetrical structures formed, but the process remained elusive until the 1940s and 1950s, when theoretical models began to connect stellar evolution with the birth of planetary nebulas. These models suggested that when a star like the Sun reaches the end of its life, it expands into a red giant, expelling its outer layers into space. The remaining core, a white dwarf, then illuminates the expelled gas, creating the glowing nebula. Yet, despite these theories, the full complexity of planetary nebulas remained hidden, obscured by the very dust and gas that shaped them. For many years, visible light telescopes could only capture fragmented glimpses of these objects, their intricate structures often lost in the haze of interstellar material. It wasn't until the 1990s, with the launch of the Hubble Space Telescope, that astronomers began to see the true scale and beauty of planetary nebulas. Hubble's sharp, high-resolution images revealed stunning details, symmetrical shapes, vibrant colors, and intricate patterns that hinted at the dynamic processes at play. However, even Hubble had its limitations. The nebula's thick dust clouds often blocked visible light, making it difficult to study the central white dwarf or the full extent of the gas and dust surrounding it. This gap in understanding persisted for decades, until the advent of infrared astronomy opened new windows into the cosmos. Infrared light, which is invisible to the human eye, can penetrate through dust and gas, revealing structures that are otherwise hidden. This capability became crucial for studying planetary nebulas, as their complex morphologies often required a view beyond the visible spectrum. The James Webb Space Telescope, launched in 2021, marked a revolutionary leap forward in this field. With its advanced infrared instruments, Webb could peer through the dense material surrounding planetary nebulas, capturing details that previous telescopes could not. The Lion Nebula, NGC 2392, became one of the first objects to showcase Webb's transformative power. Its striking, lion-like shape, once only hinted at in earlier images, was now revealed in full glory, with the central white dwarf acting as a sculptor, carving out the nebula's defining features. But this discovery didn't happen in a vacuum. It was the culmination of decades of scientific progress, each step building on the last. The journey to understand planetary nebulas began with the earliest observations, but it was the combination of theoretical models, technological advancements, and the right tools that finally allowed us to see the full story. For example, in the 1960s and 1970s, radio telescopes began to map the distribution of gas in planetary nebulas, providing data that helped refine models of stellar evolution. These studies showed that the expelled material wasn't uniform, it formed complex, sometimes asymmetric structures, suggesting that the process of a star's death was far more dynamic than previously thought. By the 1980s, ground-based telescopes equipped with adaptive optics began to capture sharper images, revealing finer details in nebulae like the Helix Nebula. These observations hinted at the presence of complex dust grains and molecular components, but the true nature of these structures remained unclear. The Hubble Space Telescope, launched in 1990, changed everything. Its ability to capture high-resolution images in visible and ultraviolet light allowed astronomers to study the intricate details of planetary nebulas for the first time. Hubble's images of NGC 2392, for instance, showed a glowing, shell-like structure with faint, wispy tendrils, what would later be recognized as the lion's mane. However, even Hubble couldn't see through the densest parts of the nebula, where the white dwarf's radiation was most intense. This limitation highlighted the need for a new approach, one that could peer beyond the visible spectrum. Enter infrared astronomy. The idea of using infrared light to study celestial objects wasn't new, but it wasn't until the 1990s and 2000s that technology advanced enough to make it practical. Infrared telescopes, like the Spitzer Space Telescope, began to explore the universe in this wavelength range, revealing hidden structures in star-forming regions and planetary nebulas. These early infrared missions demonstrated the potential of the technique, but they were limited in resolution and sensitivity. The James Webb Space Telescope, with its larger mirror and advanced instruments, was designed to overcome these limitations. Its primary mirror, 2.4 meters in diameter, is more than twice the size of Hubble's, allowing it to collect more light and resolve finer details. Webb's instruments, such as the mid-infrared instrument, MIRI, and the near-infrared camera, NIRCam, are optimized for studying objects obscured by dust, making them ideal for exploring planetary nebulas. When Webb turned its gaze toward NGC 2392, it wasn't just about capturing a new image, it was about finally seeing the full story of a dying star's legacy. The nebula's lion-like face, once only partially visible, was now revealed in exquisite detail. The central white dwarf, a scorching ember of the star's former self, was clearly visible, its intense radiation illuminating the surrounding gas and dust. This image wasn't just a snapshot of a nebula, it was a testament to the evolution of observational astronomy. Each step in this journey, from the earliest observations to the development of infrared technology, had brought us closer to understanding the processes that shape the universe. The Lion Nebula's discovery is a prime example of how scientific progress builds on the work of previous generations. It's a reminder that even the most enigmatic cosmic phenomena are the result of a long, collaborative effort. As we look at Webb's image of NGC 2392, we're not just seeing a stunning visual spectacle, we're witnessing the culmination of decades of inquiry, innovation, and discovery. The nebula's intricate structure, the white dwarf's role as a sculptor, and the delicate balance of forces that shaped it all are the product of a scientific journey that began centuries ago. Today, with Webb's infrared vision, we're able to peer into the heart of these cosmic phenomena, uncovering secrets that were once hidden. This chapter has traced the path that led to this moment, showing how our understanding of planetary nebulas has evolved from fragmented observations to a more complete picture. The next chapter will delve into the specifics of the Lion Nebula's structure, the role of the white dwarf, and what this discovery tells us about the fate of stars like our Sun. But for now, let's reflect on how far we've come and how much more there is to discover. The James Webb Space Telescope has unveiled a breathtaking infrared portrait of NGC 2392, the Lion Nebula, revealing a cosmic sculpture shaped by the final act of a dying sun-like star. At its heart, a scorching white dwarf, the remnant of the star's core, radiates intense energy, carving out the nebula's lion-like face and illuminating a sprawling mane of dust and gas. This image is more than a spectacle, it is a window into the complex processes that define the twilight of stellar life. Yet, as scientists pore over these new observations, they are confronted by a series of unresolved questions. What exactly is shaping the nebula's dramatic structure? How did the surrounding material come to take such a form? And what does this reveal about the fate of stars like our own? These mysteries are not just about the Lion Nebula itself, but about the broader story of stellar evolution and the forces that govern the universe. While the image offers a stunning glimpse into the aftermath of a star's death, it also highlights the gaps in our understanding. For instance, the precise mechanisms by which the white dwarf's radiation carves the nebula's features remain unclear. Some theories suggest that stellar winds, streams of charged particles, play a role, while others propose that radiation pressure, the force exerted by light, is the primary sculptor. But how do these forces interact, and what determines their effectiveness in shaping such intricate structures? Similarly, the origin of the nebula's dusty mane raises intriguing questions. The white dwarf's heat is likely responsible for ejecting the star's outer layers, but the exact processes that convert this material into the complex, clumpy structures observed by Webb are still under investigation. Are these clumps the result of turbulent outflows, gravitational instabilities, or some combination of factors? Moreover, the composition of the dust itself, its chemical makeup and how it forms, remains a topic of debate. While some elements are expected based on stellar nucleosynthesis, the presence of certain compounds in the nebula could hint at previously unknown pathways for element creation. These uncertainties underscore a fundamental challenge in astrophysics: how to reconcile observational data with theoretical models. The Lion Nebula's structure, for example, is strikingly asymmetric, with the lion's face appearing more defined than the surrounding mane. This asymmetry could be the result of the star's rotation, magnetic fields, or even the influence of nearby companion stars. However, the absence of clear evidence for such factors means that scientists are left to speculate. Some researchers argue that the nebula's shape is a natural consequence of the star's pulsations and the way its outer layers expand and contract. Others suggest that external forces, such as the gravitational pull of nearby objects, might have played a role. Without definitive answers, these hypotheses remain open questions, each offering a different lens through which to interpret the data. Another layer of mystery lies in the nebula's lifespan. While planetary nebulae are typically observed for thousands of years, the exact timescale of their evolution is still debated. The Lion Nebula, for instance, may have formed just a few thousand years ago, but how long will it remain visible? Will it gradually dissipate into the interstellar medium, or will it persist for millions of years? The answer could depend on factors such as the nebula's density, the intensity of the white dwarf's radiation, and the presence of any remaining stellar companions. These uncertainties are not merely academic, they have implications for our understanding of stellar life cycles. By studying planetary nebulae, astronomers hope to trace the final stages of a star's life and determine how such objects contribute to the chemical enrichment of the universe. Yet, the Lion Nebula's case adds complexity. Its unique structure suggests that the processes at play may differ from the more typical planetary nebulae, raising questions about the diversity of stellar deaths. Is the Lion Nebula an outlier, or does it represent a more common but underappreciated phase in stellar evolution? To address these questions, scientists are turning to multi-wavelength observations, combining data from Webb's infrared capabilities with other telescopes to build a more complete picture. However, even with these tools, the answers remain elusive. The nebula's intricate details, while beautiful, also highlight the limits of current models. For example, the white dwarf's radiation is known to heat the surrounding gas, but how does this energy interact with the dust to produce the observed structures? Some researchers propose that the dust acts as a catalyst, enhancing the efficiency of certain chemical reactions, while others argue that the radiation itself may be responsible for shaping the nebula's morphology. These competing theories reflect the broader challenge of integrating observational data with theoretical frameworks. Moreover, the role of magnetic fields in shaping the nebula's structure is another area of active debate. While magnetic fields are known to influence the outflows of dying stars, their exact impact on the formation of planetary nebulae is still unclear. Do they act as a brake, slowing the expansion of the ejected material, or do they amplify it, creating the complex patterns observed in the Lion Nebula? Without direct measurements of magnetic fields in such nebulae, these questions remain unanswered. This uncertainty is compounded by the fact that planetary nebulae are transient objects, their lifetimes often spanning only a few thousand years. Capturing their evolution in detail is challenging, as many of these objects are observed at a single moment in their life cycle. The Lion Nebula, however, may offer a rare opportunity to study a nebula in its early stages, when its structure is still forming. Yet, even this interpretation is not without controversy. Some scientists argue that the nebula's features may have developed over a longer timescale, with the lion's face and mane emerging through gradual processes rather than sudden events. These debates underscore the dynamic nature of scientific inquiry. Each new observation brings fresh insights, but also new questions. The Lion Nebula, with its striking imagery and enigmatic features, serves as a reminder that even in the most advanced era of astronomy, the cosmos continues to surprise us. As researchers continue to analyze the data from Webb and other telescopes, they are not only unraveling the mysteries of this particular nebula but also advancing our understanding of stellar evolution on a broader scale. The interplay between observation and theory remains a cornerstone of scientific progress, and the Lion Nebula's story is a testament to the power of curiosity in driving discovery. While the image may seem to capture a final, dramatic moment in a star's life, it is also a starting point for deeper exploration. The questions it raises about the forces that shape the universe, the processes that govern stellar death, and the role of these objects in the cosmic cycle are as enduring as the stars themselves. In the end, the Lion Nebula is more than a cosmic sculpture, it is a puzzle, one that continues to challenge and inspire astronomers to look beyond the surface of the visible and into the intricate, often hidden, mechanisms that define the universe. As we stand at the edge of a cosmic revelation, the James Webb Space Telescope's image of the Lion Nebula has opened a new chapter in our understanding of stellar death and rebirth. But this is just the beginning. The intricate dance between a dying star and the nebula it leaves behind is a story that continues to unfold, and future missions and instruments will play a crucial role in deepening our knowledge. Let's explore what lies ahead, what technologies, observations, and questions might shape the next phase of this discovery. First, the James Webb Space Telescope itself is already a gateway to new possibilities. While its current images have revealed the Lion Nebula's striking structure, its infrared capabilities are not its only strength. Over the next few years, as more data is processed and analyzed, we may uncover hidden details about the nebula's composition and dynamics. For instance, Webb's high-resolution spectroscopy could reveal the chemical fingerprints of elements being ejected by the white dwarf. These elements, like oxygen, carbon, and nitrogen, are the building blocks of planets and life, and their abundance in the nebula could tell us about the star's life cycle. If we detect unexpected isotopes or trace elements, it might challenge existing models of stellar nucleosynthesis, prompting scientists to revise their understanding of how stars distribute matter into space. Beyond Webb, the next generation of space telescopes will build on this foundation. The Nancy Grace Roman Space Telescope, set to launch in the coming decade, will offer sharper imaging and deeper surveys of the cosmos. Its ability to capture wide-field views could help astronomers identify similar nebulae across the universe, comparing their structures to the Lion Nebula. By studying these cosmic sculptures in different environments, we might uncover how factors like a star's mass, age, or galactic location influence the shape of planetary nebulae. For example, if the Lion Nebula's lion-like face is found to be rare, it could hint at unique conditions in its birthplace, perhaps a denser interstellar medium or a binary companion star that influenced the nebula's formation. Another key player in the future will be the proposed Large Ultraviolet Optical Infrared Surveyor, LUVOIR, a next-generation space telescope that could revolutionize our view of planetary nebulae. With its ability to observe in ultraviolet and visible wavelengths, LUVOIR would complement Webb's infrared data by revealing details about the nebula's outer layers. These regions, often shrouded in dust, might contain clues about how the star's radiation interacts with surrounding material. For instance, ultraviolet light could illuminate the ionized gas in the nebula's mane, showing how the white dwarf's intense radiation is carving out the lion's face. Such observations might also help us map the velocity of gas clouds, providing insights into the nebula's expansion rate and the forces driving its evolution. On the ground, the Extremely Large Telescope, ELT, currently under construction in Chile, will offer unprecedented resolution. With its 39-meter mirror, the ELT could peer into the Lion Nebula's heart with a clarity that surpasses even Webb's capabilities. This would allow astronomers to study the white dwarf's surface in greater detail, searching for subtle variations in its brightness or temperature. These fluctuations might indicate seismic activity similar to earthquakes on Earth within the white dwarf. Such oscillations, known as asteroseismology, could reveal the star's internal structure, much like how geologists study Earth's core. If the white dwarf's oscillations match theoretical predictions, it would confirm our understanding of these compact stellar remnants. If not, it could lead to new models of stellar evolution. But the story of the Lion Nebula isn't just about the star and its immediate surroundings. It's also about the broader context of stellar death in the universe. Future missions like the Spica Space Telescope, a Japanese-led infrared observatory, could shed light on how planetary nebulae contribute to the cosmic cycle of matter. By studying the infrared glow of these nebulae across vast distances, Spica might quantify how much material is being recycled into interstellar space. This data could help us estimate the role of planetary nebulae in enriching galaxies with elements necessary for star formation and planetary systems. For example, if the Lion Nebula is found to contain unusually high levels of heavy elements, it might suggest that its progenitor star underwent a unique fusion process before its demise. Of course, not all discoveries will align with our current theories. The Lion Nebula's structure, while dramatic, might raise questions that challenge existing models. For instance, if future observations reveal intricate filaments or unexpected symmetry in the nebula's shape, it could suggest that external forces, like magnetic fields or interactions with nearby stars, play a more significant role in shaping planetary nebulae than previously thought. Similarly, if the white dwarf's radiation is found to interact with the nebula in ways that defy current simulations, it might prompt a re-evaluation of how stellar winds and radiation pressure influence these cosmic sculptures. Such surprises are not only inevitable but also essential for advancing our understanding. Moreover, the study of planetary nebulae like the Lion Nebula could have implications beyond astrophysics. By analyzing the chemical composition of these nebulae, scientists might gain insights into the conditions that led to the formation of our own solar system. For example, if the Lion Nebula contains traces of molecules like water or organic compounds, it could hint at the role such nebulae played in seeding the ingredients for life. While this connection is speculative, it underscores the broader significance of these cosmic phenomena. The Lion Nebula is not just a beautiful image, it's a laboratory for understanding the origins of the universe and the processes that shape the cosmos. As we look to the future, the integration of data from multiple observatories will be critical. The Lion Nebula's story is a microcosm of the larger narrative of stellar evolution, and by combining observations from space and ground-based telescopes, we can piece together a more complete picture. For instance, while Webb's infrared data reveals the nebula's structure, ground-based telescopes could track how its light changes over time, offering clues about its dynamic evolution. Similarly, space-based ultraviolet telescopes might capture how the nebula interacts with the interstellar medium, shedding light on its role in the galactic ecosystem. In the coming decades, the study of planetary nebulae will likely become even more interdisciplinary. Advances in computational modeling, coupled with high-resolution observations, could allow scientists to simulate the Lion Nebula's formation in exquisite detail. These simulations might test hypotheses about how the white dwarf's radiation shapes the nebula's geometry or how the ejected material interacts with surrounding gas. If simulations fail to match observational data, it could lead to breakthroughs in our understanding of stellar physics. For example, if the nebula's lion-like face is found to be the result of a complex interplay between magnetic fields and radiation pressure, it might inspire new theories about how these forces influence the final stages of a star's life. Ultimately, the Lion Nebula's discovery is a testament to the power of modern astronomy to reveal the universe's most dramatic processes. But it is also a reminder that our understanding is always evolving. Future missions and instruments will not only refine our knowledge but also challenge us to think creatively about the cosmos. As we peer deeper into the universe, we may find that the lion's face is just the beginning of a story far more intricate than we can yet imagine. The Lion Nebula is a beacon of what lies ahead, a symbol of the endless quest to uncover the secrets of the stars. James Webb has captured a striking new infrared view of NGC 2392, the Lion Nebula, revealing the dramatic aftermath of a dying sun-like star. At its center, a scorching white dwarf is blasting radiation into surrounding gas and dust, carving out the nebula's lion-like face while illuminating a sprawling mane of surviving dusty clumps. This part of our deep dive into James Webb captures a cosmic lion sculpted by a dying star focuses on, briefly recap the 2 or 3 biggest takeaways from this deep dive in a satisfying way, then invite the viewer to subscribe to FactVerse for daily space deep dives and to comment their own theory or question. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable.